Welcome to the presentation of our tool for modeling a hardware platform for safe deployment. We provide an abstract and concrete syntax for the modeling of a hardware system so that an automatic deployment can be specified. Our tool is part of the Fujava real-time tool suite for the model-driven development of cyber-physical systems. For the demonstration of our tool, we use a cooperative adaptive cruise control system as a running example. Consider a car which is equipped with such a system. The system supports the driver by adjusting the speed to maintain a safe distance to a preceding car. Therefore, it measures the distance to the car in front via a radar sensor. Moreover, the cooperative adaptive cruise control system exchanges information via wireless connection between the cars. For instance, the front car sends a warning to the rear car about obstacles ahead of it. For prototyping such a car, we built the described system with the open source hardware Arduino. The distance to the preceding car can be measured via a distance sensor, and the car-to-car communication is realized via a Wi-Fi interface. Our Arduino car is composed of three subsystems: the powertrain, the assistance, and the telematics system. The powertrain system is responsible for the driving behavior of the Arduino car. It consists of an Arduino Uno board, which is coupled with a CAN shield to connect the powertrain system with the other subsystems, since the Arduino Uno board does not provide a CAN interface. Moreover, the Arduino Uno is coupled with a motor control shield, which enables the controlling of two DC motors. The next subsystem is the assistance system. It maintains the distance to a preceding car by measuring the distance and adjusting the speed. It is assembled of two Arduino Duo boards. One of them is connected to a distance sensor, where the second coordinates the assistance, the powertrain, and the telematics system. The last one is the telematics system. It consists of an Arduino Duo board, which is coupled with a Wi-Fi shield. The Wi-Fi shield allows the exchange of data between cars. The modeling of a hardware platform like our Arduino car is classified into two main viewpoints to separate different concerns. The first viewpoint is the resource viewpoint. Based on the product datasheet, the general types of a resource and the general attributes are modeled. In our case, the resource type Arduino board, its memory and processor are modeled. Next, the resource type is instantiated and parameterized. For our Arduino car, the Uno board, the Duo board, and their clock rate and size of memory are specified. These information are later used for worst-case execution time analysis and to determine a safe deployment of a software system. The second viewpoint is a platform viewpoint. Within the platform viewpoint, the horizontal and hierarchical composition of a hardware platform is modeled. For our Arduino car, at first the different subsystems, powertrain, telematics, and assistance are modeled and then hierarchically composed to the Arduino car. We start the modeling of our Arduino car by modeling the resource type. First, we model the resource type Arduino. It consists of a memory of kind RAM and a memory of kind flash. Furthermore, it has an embedded ARM processor. Moreover, the Arduino board can be coupled with several shields which extend its behavior. At first, the Arduino board has an optional CAN shield which uses the CAN protocol. Secondly, a motor shield which is able to control up to two DC motors. Furthermore, the Arduino provides up to 22 possibilities to connect different sensors via digital ports. At least an optional Wi-Fi shield can be attached to the Arduino board. Furthermore, a motor, a sensor and their hardware ports are modeled. Finally, the resource CAN bus of the Arduino board with a given bandwidth of 1 megabyte is specified. After the resource types have been specified, we instantiate the Arduino Duo board. It has a RAM size of 96 kilobyte, a flash memory of size 512 and a clock rate of 84 MHz. The Uno board is instantiated similar. The Duo board and the Uno board differ in the size of the memory and the clock rate of the processors. After the resource instances are specified, we can compose them to a hardware platform. So let's see how the hardware platform for the powertrain subsystem looks like. Since the powertrain system is composed of a single Arduino Uno board, we create a resource part and type it over the Arduino Uno board. Moreover, the powertrain consists of two motors. Thus we create a part of type motor and assign it a multiplicity of 2. Both motors are connected to the Uno board. Finally, the system provides a CAN interface to the outside, which is represented by this port. The assistance system is created similar. It consists of one or two Arduino boards of type Duo, which are connected to a distance sensor, and it provides a CAN interface to the outside. Furthermore, the telematics system is modeled. It consists of a Duo board, which enables the car-to-car communication. Therefore, it provides a Wi-Fi interface to the outside and a CAN interface for the internal communication. Finally, the platform Arduino Car is composed of the former specified platforms: the mandatory powertrain system, the optional assistance system, and the optional telematics system. The systems are connected via a CAN bus to enable the internal communication. Finally, a concrete platform instance of the Arduino car is created. The concrete platform is instantiated based on the former specified multiplicities. For instance, a Arduino car including the optional assistance and telematics system. Here we see the automatically created instance of the Arduino car and its subsystems. Thanks for watching our video. We invite you to make your own impressions by trying out our tool. You can install it via our Eclipse update site. In the future, our tool will be extended by allocation planning and safety analysis features for a safe deployment.